Okay, this question again asks us which one of these protons is more acidic. It actually shows us some protons. In the first one, I went ahead and drew in the other proton. Now remember, both of these protons are going to be equivalent. Then the structure, it only showed you one. I didn't want there to be any confusion. It is an alkene. There are two protons attached to that terminal carbon. It's just considering, okay, consider one of these protons, which one, is it more acidic than the proton in 2 or 3 or 4? So remember, in order to consider which one of a proton or a species is more acidic, you really are considering the strength, you really are considering the stability of the conjugate base. So we have to draw the conjugate bases. So we have to draw the species that would result when the species behaves as an acid. So when this proton is donated. So for one, it's like this. I have a proton, one of the protons at the vinylic position is donated, and that means I have a vinylic anion. Here I would have, for 2, I have a carboanion. So that hydrogen is donated and the lone pair moves back to the carbon. Same thing for 3. It's just a slightly different structure, still as a carbon-based anion. And of course, the same thing is true for 4. It's a carbon-based anion. It's just a little bit different structure. So they've got some differences going on around which carbon and what's going on near that carbon as far as the conjugate base is concerned. So let's take a look. When we consider conjugate base stability, we typically consider the atom, we consider resonance, we consider induction, and we consider orbital. One of the things that we know about orbitals is that vinylic cations are typically more, sp2 orbitals are typically more acidic than sp3 orbitals. And so you might think that then 3 is less acidic than 1, and that's going to be true. But you might also look at that same argument and say that, well, doesn't that make 2 and 4 less acidic than 1? And the answer is no, that's not true. Yes, there are some orbitals considerations to be made, but usually the order that this takes place, this precedent in, is in the order of atom, resonance, induction, and orbital. So orbital is usually the least important factor. So in this case, all things aren't equal. Now, we're going to go ahead and eliminate atom because remember, we're talking about carbon-based anions in every case. So that's not what's going on here. Let's take a look at what is going on here. It turns out that in 2 and in 4, I can show a resonance structure where the electrons can be delocalized. So it's important to then go ahead and consider the resonance structures that are able to be drawn. So let me go ahead and draw a resonance structure where the double bond looks there, and I now have an anion at that terminal carbon. Same thing over here. I can throw the double bond will be positioned in the middle. Instead of a terminal carbon, though, I have a terminal oxygen. Okay, so now I've got 2 resonance structures shown. And so in this case, it looks like 2 and 4 are going to be a little bit more acidic than any of the other ones because there's resonance stability in the conjugate bases. Now we got to think about the difference between 2 and 4. Which one is more stable as a conjugate base? Well, we know that they both have resonance, but let's take a look at let's bring back atom now. Which of the resonance structures show the negative charge delocalizing to a more electronegative atom? Well, it's 4. It delocalizes in exactly the same way, but the charge ends up on an oxygen rather than on another carbon. So it's a combination of atom and induction. In 4, I've got a electronegative oxygen that's near, not exactly next door, but near the proton that we're considering versus a carbon. But what's really playing the most important thing is resonance. And when I think about resonance, I'm thinking about what's the other atom that the charge delocalizes to? Well, in the case of 4, it delocalizes to an oxygen rather than a carbon. So if I were to say which one is the most acidic, it's 4. So that's number 1. What's the next most acidic? Well, it's the other one that has resonance. That's number 2. And then I don't have resonance to consider for the next ones. So it's just based on our ideas of pKa and orbital. And that means that the sp2 orbital is more acidic than the sp3 orbital. And so it would look like this. Okay, we figured out number 1, and we also were able to put them in order. That's it.